This is the only Korean I know. Sorry. And it's a great pleasure for me to be here today to talk about the importance of the molding and its technique. And I hope my presentation will give some hint for you to improve your molding technology further. I will talk about several topics, including why do we have to focus on molding first, and then I would like to talk about molding as current practice, and then I have some thoughts for you for the practices for the better molding. And finally, I would like to present some recommendations, and I would like to invite some questions. Let's talk about the first topic of why do we have to focus on the molding. This is their effort production back in 1996. This one for all the major Asian countries. The total production by ethylene 90 million tons a year. And as you can see from this slide, Japan has the largest market for it, and then followed by Korea and China. And this is the market share 10 years ago. This is a prediction by the Japanese government for the year 2008. So in 2 years' time, this will be the real picture in the market. Which is surprising because the total production will be almost 4 million tons a year, so double. Unfortunately, Japan remains its capacity, so I think Korea is planning to increase the capacity these days. So in 2 years' time, the largest producer will be China, ASEAN, Korea, and Japan. And I hope the modeling will be the key to the differentiation of the different countries, the different companies. I would like to explain the modeling practice as the current activity. This is the old diagram for the market field diagram, and maybe those who are younger engineers may not familiar with this diagram, but this is technology back in 1970. We had to use this kind of diagram to design distillation columns such as acetone water dialysis. And this technology was limited to the binary system, two-component system, and we couldn't consider the heat balance. We consider only the mass balance. And this was a graphical method. So if you have the VLE like this, very close to operating line, then accuracy depends on the accuracy of the VLE. So the graphical method didn't give us the high enough accuracy back in 1970. And today, well, this is the 1990s technology. We enjoy their quite a big improvement from this innovation. This is a model of the distillation column today. We can consider heat to the trays and side draw, decanter. We can also consider data display. So we can consider the many operating conditions these days. The difference we have is the multi-component, space-to-space calculation, heat and mass balance calculation, and we can also use three-phase distillation calculation. Let's consider about the VLE model, how we have made progress in representing the VLE. This is acetone chloroform VLE, which is known to be very difficult to represent. Back in 1970s, we can find empirical activity coefficient model was used quite extensively. This is Margol's equation, and we can see this Margol's equation reasonably fit well to the measured data of the PFEED. But if you look at more closely about the accuracy of representing the PXY diagram, then we can find a big difference, errors, in correlating the result. So these are the errors in correlating the PXY diagram. So as a result, the new more rigorous method was developed by Proudnitz, and this is the uniquark equation. And there are many parameters, but using this more rigorous method, we can now rigorously represent PXY diagram of acetone fluorophore system. So again, we are now enjoying the benefits from the development of the technology for the last 20 years. So I would like to mention that modeling and current practice, we are getting benefit from the rigorousness to represent data. So every day, all the engineers in the industry is using this process simulator to calculate this rigorous level. And my topic today is relatively related to the another aspect of these modeling methods. I would like to briefly explain the shortcomings as well. The first one is if you want to use a model like uniquark, we have to prepare many parameters. And also, I would like to discuss the shortcomings related to numerical calculation orienting. Because computer has progressed for the last 20 years, we can now calculate very complex calculations. But at the same time, there are things we have to do before we start a numerical calculation. So I would like to touch on these two points. Regarding the practices for better modeling, firstly, I would like to talk about reducing the number of the parameters and then two things before numerical calculation. Let's talk about the Antoine equation as an example related to the number of the parameters. I guess everyone in this room is familiar with Antoine equations, which is related to vapor pressure representation. Suppose we have a vapor pressure measurement, like the temperature versus vapor pressure. We have some errors, of course, in this experimental data. There are actually many equations available to represent vapor pressure. And the most well-known one is Antoine equation. And Wagner equation is also well-known, which is applicable close to a critical point. Differ equation is also familiar. And extended Antoine, this is in case of the Antoine plus representation. So we have these equations. And I would like to show the comparison of Antoine equations and extended Antoine. And in case of their Antoine, I just set C equals to 0 so that we can have only two parameters for the correlation. And in case of extended Antoine, I just use the parameters from A through B, a 5-parameter equation. If we use 2-parameter Antoine equation, we can correlate the measured data, but of course we can see some errors here. The error comes from not only from the equation itself, but come also from the error of the experimental data. If we use extended Antoine, we can regularly represent all the measured data here. So in this sense, 5-parameter equation is more rigorous. But if we extend the calculation beyond the range of the measure, then we have this quite strange behavior. So if we use too many parameters, it's quite tricky to extend correlation outside the range of the correlation. Another example for the number of the parameters is I would like to use the vapor-liquid equilibrium. This is acetone chloroform data I used just now, and we know that this is a difficult system to correlate with the empirical mode such as markers. And UNIPAC was applied successfully to represent the data rigorously. I would like to explain the feature for the background of the UNIPAC model, which is related to Wilson and Elliott as well. We have vapor and liquid, the phases here. And in vapor phase, we have uniform molecules are randomly placed like acetone and chloroform. But in the liquid phase, these equations have some assumption that liquid phase is not in uniform. So around the acetone molecule, we have more chloroform. And around the chloroform, the molecules, we have more acetone. So in this sense, no ideality of solution attributed to a difference of local composition around molecules. So we call this model the local composition model. We have alternative approach, which is called the chemical theory. In the case of chemical theory, again, we assume uniform in the vapor phase. But in liquid phase, we also assume this liquid phase in ideal. Ideal, but with ternary system. 3 components: acetone, chloroform, and associated compound between acetone and chloroform. So instead of assuming the composition being locally different, we use the assumption that the solution itself is ideal. We just need to consider all the 3 species. So considering all true species resulting from association allows us to model the system as ideal system. These are the equations to represent this system. First 3 equations are Raoult's law. We learned at the university that these 3 equations. And then the next 2 equations are sum of the composition are equal to unity in vapor phase and liquid phase. We just consider the association reaction in this liquid phase using the mole fraction of 3 components. And of course, these are Antoine equations to represent vapor pressure. And we assume associated compounds being non-volatile. We just consider a volatile component for acetone and chloroform. And we can assume equilibrium constant being 5, for example. Maybe 5 is not appropriate, but let's try to calculate using this with the 5. And we can also use the measured temperature. So these are the equations, and I hope these equations are not complicated to you. And we just use Raoult's law, sum of the composition. We just introduce the association equilibrium. And these are Antoine equations, which are familiar to us all. In this case, we use ease, which is the true mole fraction of 3 components: acetone, chloroform, and associated molecules. But we are more interested in X, I mean the mole fraction of the acetone. So we, of course, for the calculation we need mole fraction of 2 species, but we are more interested in the X. So this is the relationship between true mole fraction and apparent mole fraction. Suppose we have 1 molecule of acetone, 3 molecules of chloroform, and 2 molecules of associated compound in the liquid phase. When we sample the liquid, we usually use gas chromatography for the analysis. And if we put heat to this sample, then this associated compound will be dissociated because of the heat. So we now have actually 3 molecules of acetone and the 5 molecules of chloroform. So as a result, when we measure the composition by gas chromatography, what we observe is X1 and X2, which are different from true mole fractions. So we are more interested in this phase. By having this explanation, we can now convert E's to apparent mole fraction. The total molecule, number of the molecules are E1 and E2, but we need to double the number of the molecule for the E3 because it will be dissociated into 2 molecules. So we need this factor. For this one, all the acetone-related molecules, we have acetone, but we also have acetones here. So we also need to consider this. So this is the conversion the equation of the true mole fraction to apparent mole fraction. By having these equations, we can now calculate actually this. If I use K being 0, K being 0 means we have 2-component system, ideal system, strictly ideal, or strictly strict system with their Raoult law. So we have this diagram. The XY diagram is very close to a diagonal. But if I use K being 1.5, suddenly the system exhibits the non-ideality. Although we use the ideal calculation, we just included the chemical reaction in the vapor equilibrium. If I change K, we have different the curves. And now we can have a better understanding that K being 1.5, very close to the major phase. But as a result, for the XY diagram and the PXY diagram, surprisingly, PXY diagram is reasonably well represented with ideal equations. So one adjustable parameter. In this case, remember, we just used K as adjustable parameter. In case of modulus, we saw the first, we used 3 parameters. In case of uniquark, I don't know how many parameters I have to use. But in this case, just one adjustable parameter with single, and also this parameter. The uniqueness of this method is this parameter has a physical meaning. If we use modulus or uniquark, we don't know the parameter's meaning. But if we use this chemical the theory, the parameter we use is much less, and also this has the physical meaning, which is very actually beneficial for the engineers. And the next topic I would like to talk about is here 2 things before numerical calculation. Today we enjoy the power of the computer. We can calculate a very complex flow sheeting using Pro2 or Aspen Plus or Gcron. But I would like to stress that there are things we have to do before starting numerical calculation. Well, let's consider very simple reactions, or 2 complex, or 2 reactions. A plus B forms C, which is the desired product, and B plus B forms D, which is impurity. And well, suppose we are at the early stage of R&D, so we don't know exactly the rate constant yet. But we would like to consider the reaction process to maximize C and minimize D, because C is the main product. We want to maximize C. but we don't want to have D. We want to reduce D. But we don't know the rate constant yet. What should we do? One idea is just start a numerical calculation. In order to do a numerical calculation, we have to assume K1 and K2 for the two reactions. And we have to determine the flow sheet. Let's suppose that CSPR, continuous serotonin reactor, and number of stages. And of course, we have to determine the A and A to B molar ratio at the feed. We also need to determine the conversion of A, and which will allow us to calculate the residence time. So if we want to start numerical calculation, we have to determine all these things. And then we can calculate. And this was a trial simulation. And of course, in order to find the optimum point, we have to run many more cases. So should we vary K1, K2, number of stages, molar ratio, conversion to A, etc. We seem to have too many assumptions. And we want to have probably a better approach. One better approach would be analytical approach before numerical calculation. We can derive differential equations based on these two reactions. Even if we don't know the K1 and K2, we can derive these differential equations to describe the changes in A and B. Dividing these two equations by themselves give us this equation, differential equation. And this is the linear differential equation, and actually we can solve this equation analytically. This is the result. The result seems very complex, but the important point is parameter is the K2 to K1. So as long as we select K1 to K2 value, then this determines the reaction performance. I think this kind of analysis that gives us a better understanding of the process. Before we use numerical calculation, and that also gave us some information. But this approach, analytical approach, also gives us the better understanding. But this is not everything we can do. We can also consider equations even before solving them. The previous step, we solve the equation analytically. But let's consider, can we find more information before solving them? So again, we have these two differential equations. We are more interested in C and D, because C is the main product and D is improved. And we can derive differential equations for C and D. By dividing these two equations by themselves, we have this differential equation. This equation means while the reaction takes place for the increase of D, we can also calculate increase of the C, which is the main product, by having this information. And having this information, the K1 to K2 value, but also A to B ratio is important. So what is required to maximize C to D? To maximize C to D, we need to maximize this term, right hand. So A to B must be maximized, and B to be minimized. Then we can draw the conclusion that B must be added by small portions, not added at the same time with A. This equation tells us that this is the way we should construct the process. So by having these approaches, started from the numerical calculation, then analytical solution, then interpretation of the equations themselves, our understanding is becoming the better and better. And actually, these approaches they gave us a much better understanding than before. And this is the industrial practice for the alkylation. This is the A plus B to form product, and B to B to form byproduct. So in a sense, this is the same manner. And we can see actually the feed, A is fed at this point, but the B is fed separate. So we cannot apply these equations rigorously to this process because this is a gas absorption process, including the absorption. However, the interpretation of the approximate equations can give the right answer for conceptual design. So even without numerical calculation, we can actually consider this kind of the configuration if we consider to interpret what the equations mean. Finally, I would like to make some recommendations. English saying is, if the only tool you have is a hammer, then you will treat every problem as a nail. There are many activities, actually, for carpenters, but if the only tool you have is a hammer, then you have to use hammer for every task, which is ridiculous, of course. But simulator is not the only tool you have. I think it's very important for us to use appropriate methods. Experimental work is of course important for us to use to build a model. And of course, simulator is very helpful. As we saw at the beginning of my presentations, there are tremendous development and progress in calculation using the process simulator. And this is very beneficial, and I have no doubt that for the future, we will continue using the process simulator. So process simulator gives us the important the benefit. But finally, I would like to focus that our own modeling is also important. By us putting our effort to build equations, try to interpret, and try to build a model with less parameters. These are the keys to build the better the modeling on top of these two activities. So, and equation solvers can help you model various problems these days, and unfortunately, I don't have enough time to show the demonstration. But I can show the demonstration if some of you are interested in after this morning session. Okay, thank you very much for your attention.